How all we are, how all we are, how are we all?
How
Alays.
old we are, how old we are, how are we all?
Sorry about that. Echo again. It always comes up with an echo first time around. How are we doing, guys? How are we doing? It's Monday. Hopefully, you haven't lost the enthusiasm that I was met with last week, and you're still up for making sure you're finishing all this AS content. Um, Hey Salma, hey Ruhab, what do you need help with? Hey Miracle World, Faye, Benyon, good to see you guys back again. I was going to say, Ruhab was just like, help, Rich. Hey Louis, how are we doing? Who have we got that's new today? I want to just make yourselves known to me. I want to welcome you and make sure you've got everything you need. Hey Baked Team, Mimi, welcome back, guys. Good to see you guys again. Louis, you're new. Welcome. Very much welcome. How are you doing? So yeah, year 12. What are we going to do? Well, we've got to finish the spec. That's what we've got to do. Will the exam response videos be free next week? No. All right. So we're just giving out some content guide videos and stuff like that. So for the TT method, I think, if you're going to be using the exam guide stuff for your TT method, then, you've always got access to the mark scheme. But I think, that's something we're going to obviously maintain for our subscribers. So as a subscriber to the exam guide, you get our explanations and our in-depth, accounts of, if you like, for each of those questions. So yeah, I mean, for now, what we're trying to do is just finish the spec. And I think content guide videos are the way forward for that. So at the end of this session, I haven't done it yet, but at the end of this session, I'm going to unlock parts of the enthalpy section for you guys. So Louis and anybody else that's new, if you haven't already joined the Exambulance, you can do that by going to our TT website, tailoredtutors.co.uk, and there's a big white block right at the top of the homepage that says Exambulance. You've got biology, chemistry, maths. Just sign up to it. It's absolutely free. We're just giving you guys a framework to help you finish the AS content. So in there, we've got like that schedule of all the lives and everything that we're doing on YouTube. And of course, like I said, and I do every day, once we finish this session, from within the Exambulance in the top section, you can click a button, AQA content guide, OCR EdXL content guide, and you will see little unlocked padlocks for the sections that I've unlocked for you. And not every video in there is unlocked, but the major ones that I think you guys need to have a look at. So they're going to be open up for the next 24 hours. So, it won't take you long, maybe half an hour to 40 minutes to watch all those videos, make your notes, do what you need to do. So we're just giving people access because we know you guys been landed in the SH1T, just like everybody else. And, all the media and stuff's around year 13 and what's going to happen to their grades. We want to look after you guys in year 12 because you've been pretty much abandoned by the education system through no fault of anybody's. Obviously, it's just the way it is. And yeah, so that's what we're doing. Will there ever be a coupon? Who knows? We're talking about coupons and stuff right now. We don't know what to do for the best to help students out. So watch this space. We'll kind of get through this finish the spec for you guys for the AS over the next few weeks, and we'll see where we're at from there. So what I do know is that at some point, any year one subscribers, if you subscribe to a year one course, at some point, we're going to click a button, and then anyone that's subscribed to year one will get access to the year two course as well. Okay, and we're just trying to help students kind of finish the AS content and get ahead on the year two. Don't know when that's going to be yet, but that's something we do every year. And if you're a year one subscriber, obviously it's cheaper subscription. If you keep your year one subscription through the summer and you don't break it, then you continue just to pay that lower price for year one into year two, but you do get all the year two stuff. So just rewarding people that are with us from year one into year two, and we just make that cheaper and give you stuff earlier than everyone else. Okay. Not just for a week, Ruhab, it's a monthly subscription. So let me just say hi, HJB, Dennis and Miss C, how are we doing? So yeah, so that's the way we play it. Okay, that's what we do every year for our year one subscribers. Is if you continue your year one subscription into year two, then you don't have to do anything. We just unlock the content. You keep paying the same price. Okay. So enthalpy, ladies and gentlemen, on a scale of 1 to 10, okay, I want you to rate enthalpy for me in that section of the course. So 10 being, you know what? on a scale of how easy you find it, 1 being really, really easy, 10 being really, really hard. So scale it for difficulty for me, please, guys. So 1 being really easy, enthalpy, and then 10 being really, really hard. Salma's given it an 8, Megan's a 7, Benion's an 8. Oh, right. Okay. So a lot of you find this quite difficult. Okay. Oh, apart from Merrifield World in there with a 1. Yeah, it's a walk in the park. Okay. That's fair enough. Okay. HJB saying it's probably the hardest thing that you've ever done. That's cool. I mean, it is tough. It's hard to get your head around to start with, but what I really think I'm going to help you with today is your understanding of what enthalpy is. Okay, so yeah, fairly high numbers there, which doesn't surprise me. It is quite tough. I think when I used to teach, I used to spend a good amount of time on this, making sure that people knew the pracs, making sure students understood exactly what enthalpy is, because I think, we all get bogged down with the calculations and stuff. But to have that underlying knowledge of like, yeah, I know exactly what enthalpy is. So this is what we're looking at. Let me just share my iPad with you guys. So I've just summarized very briefly exactly what I believe is included in enthalpy. So here we've got 5 sections. First of all, what is enthalpy? We're going to have a go at that. We're going to talk bond enthalpies as well. Calorimetry, that's the practical side of enthalpy. We got these little things we need to know about called enthalpy or energy profile diagrams. They're a walk in the park, I think. I can explain that in 2 minutes for you guys. And then Hess's Law. Hess's Law probably, I would say Hess's Law is the one thing that, of all the things in enthalpy, that students do find the most difficult. Okay, so hopefully we're going to spend a good amount of time of what we're doing today on that. So I'm going to give you like a best of, like a headlines thing, and hopefully it's going to just reassure you on the things that you do know about enthalpy, and hopefully give you some insights and some little eureka moments as to things you didn't know about enthalpy. Okay, so first of all, what is enthalpy? Well, enthalpy is basically H. That stands for enthalpy because, of course, we talk about delta H, and that's the difference in enthalpy. Something we can't do is measure the enthalpy of a substance directly. Okay, it is a measure of energy. You're right there. Absolutely. It is a measure of energy. So let me just say that we have got a Coke can. Okay, so there's a hole in the top of the Coke can and there's a certain amount of water in it. Okay, now we can't see inside it. We don't know how much water's in there, but what have we got a way of, we can't actually see how much is in there. Okay, we can't actually see how much is in there. Then we pour a little bit out. Okay, and we end up with the same Coke can, okay, but with a different amount of water in. So let's say we can't see in these cans, okay, just like we can't tell how much energy is encapsulated, if you like, inside molecules. So imagine this is a molecule. Let's say this is CH4. We can't actually see what's inside it. But if that changes, if the amount of energy in there changes, okay, during a reaction, let's say you burned it and you ended up with CO2 and H2O, we don't know how much energy is in here either. Okay, so we don't know how much we started with in terms of chemical energy. We don't know how much we ended up with, but actually what we can tell is the difference between the two, and that is enthalpy change. So it's like it's a measure of energy. Okay, we cannot measure the amount of energy contained within a chemical directly, okay, whether it's the reactants or the products. But what we can tell is that during a reaction, there's a change in energy. There's a change in enthalpy, okay? And that's why we calculate delta H all the time, okay? It's the change in enthalpy for a particular reaction, okay? We measure energy change, yeah, energy transfer, if you want to call it that, T-Boy, absolutely. Okay, so that's what we're trying to do with enthalpy, is measure energy changes of reactions. Of course, at GCSE, we used to label these as exothermic and endothermic. Okay, so this is, of course, measuring heat energy, how much heat energy is released during a reaction, or how much heat energy is taken in during the reaction. Okay, so in an exothermic reaction, is heat energy lost or is it absorbed? One word, please, guys. Lost or absorbed? That's what I'm asking you now. So in an exothermic reaction, is it lost or absorbed? Good, absolutely. Okay, so energy out. So it is lost during the reaction. So heat energy out, of course, endothermic is in, and it is absorbed during the reaction. So to use my Coke can analogy, let's say we started with this much water in there. During an exothermic reaction, okay, let's say for argument's sake, if I've got this much water in to start with, is the water level going to be higher or lower when we get to our products? Okay, so in an exothermic reaction, if water is the amount of energy that's contained within that Coke can, what happens to it in our products? Good, absolutely. It's going to be lower, okay? Because what happened to all of this energy in here? Well, it got released to the surroundings, okay? So we end up with less energy in our products than we started with in our reactants, okay? So what you've got to have in your mind is this, well, I use this analogy in my head all the time, right? So energy's been lost, so there's less chemical energy in the products as there are in the reactants. And that's what happens in an exothermic reaction. In an endothermic one as well, just to kind of make this clear, we start with less energy in our products, in our reactants, and then we have more energy in our products because energy has actually been absorbed. So our products may contain more energy than our reactants. Okay, so this is what's going on. Now, like I said, we don't know how much we started with or how much we finished with, but what we do know is the difference. Okay, so how much energy was absorbed or how much energy was released. Okay, so that's why we talk about delta H all the time, all the time. So onwards and upwards. I don't want to spend too long on that. So let's think about it in terms of bonds. Okay, so let's say we've all done this because this is GCSE, ladies and gentlemen. Okay, so we have got a reaction here. This is just like combustion of methane. We end up with carbon dioxide and H2O. Okay, so how much H2O are we going to get? We're going to get 2 H2O, and I think that is now balanced. Okay, so mean bond enthalpies. Mean bond enthalpies are measured because measured in such a way that, okay, we're going to see bonds all the time. Okay, so like CH bonds or C double bond O's and so on and so forth. Their average or their mean bond enthalpies, because they are slightly different depending on what molecule they're in. So for example, an OH in water might be different to an OH in an alcohol, or slightly different to an OH in a carboxylic acid. So what they've done to find the mean bond enthalpy is taken all of those actual values, how much energy it takes to break a bond, and averaged it out. Okay, that's what they've done. Hey, so talk about mean bond enthalpies. A bond enthalpy is always a positive value because it's the amount of energy, the average amount of energy it takes to break 1 mole of those bonds in gaseous molecules, okay, at standard conditions. So what we're looking to do is actually give a number to a CH bond, for example, an O double bond O. How much energy does it take to break 1 mole of those bonds, all right? And yet, T-Boy, absolutely. So to find the overall delta H of a reaction, okay, it's a balancing act, all right? And it totally dictates on whether a reaction is exothermic or endothermic. So bond breaking. This is the way I do it. Bond breaking. So in a typical question, they'll give you all the different values. Yeah, breaking a pencil requires energy. Absolutely. Not that I'm going to break this one, but yeah. Okay, so to break bonds requires energy because there's an electrostatic attraction there. Okay, the bonds are formed. Those two atoms are attracted to each other. In order to break that, in order to pull them apart, you need to put energy in to do so. Okay, so bond breaking, all of these are positive values. Okay, oops. So all of those are positive values. So this is how I do these calculations for mean bond enthalpies. So if I was adding up, I'd have 4 CH bonds, and I'd have 2 O double bond O bonds. Okay, so that's what I'd add up there. I don't know, let's say that was plus, I'm just making these numbers up, by the way, guys, plus 50, and maybe this is 150. Okay, now bond making on the other side. Now, bond making is an exothermic process. Think of it like when two things come together, whether it's an intermolecular force or whether a bond forms or whether it's between positive and negative ions when you form an ionic lattice. Whenever you get two things attracted to each other, boom, energy is released. It's almost like, oh my God, I've got loads and loads of energy. I need to release this energy. Oh, I'll bond to something, and then all that energy gets released, and these are in a lower state of energy. Okay, so it's kind of like, you know, when they're on their own, they're unstable. When they join together, they stabilize and then release energy to the surroundings. Okay, so anything, whether it's any sort of electrostatic attraction, so whether it's something positive to something negative, when you're forming a covalent bond, when you're forming an ionic bond, when you're forming an intermolecular force, okay, energy gets released. So as a consequence, of course, all of these are negative values, and we'll talk about delta H in a sec. So here we've got 2 C double bond O's. So let's say that's minus 110. And we've got 4 times OH's. And let's say that's minus 250. Okay, so you can see how I've put positive values there and negative values there. Now, how do we work out the overall delta H for this reaction? Well, it's literally just a case of putting all those numbers together. If you set it up like this, you know, some people say, oh, well, it's products minus reactants and this, that, and the other. Bond breaking minus bond making, or yeah, that way around, whatever you want to remember. But for me, this is the way I teach it. I think this is the easiest way to do it. Just ascribe positive values, everything to bond breaking, negative values to everything bond making. So delta H would be 50 plus 150 minus 110 minus 250, and I have no idea what that gives me. So that's 200 minus 110, which is 90. So 90 minus 250 equals minus 160. So that would be the overall delta H for that reaction. Okay, it's by far, I think, the easiest way of doing these. Okay, so what does this tell you? What does this tell you about the overall enthalpy change for this reaction, ladies and gentlemen? What does that number tell you? Good, T-boy. Absolutely is. And Miss C, it is exothermic. The reason, okay, it's because it's negative. Okay, so if delta H, a negative delta H is exothermic, a positive delta H is endothermic. All right. Now, the reason is this. Let's go back here. You see how we're measuring the amount of energy within a system. This is our level in our products, okay? Sorry, in our reactants to start with, okay? Now, an exothermic reaction, go away, Siri. In a reaction, this exothermic reaction, you can see that from where we've started, the amount of energy within the system, the chemical system, has gone down. It's gone negative, okay? So that's why a negative delta H equals an exothermic reaction. Here you can see that, if my line's rubbish, okay, that we've increased. This would be a positive enthalpy change. So think of enthalpy like the amount of energy in a chemical system. In an exothermic reaction, from where you start in the products, we don't know where that is, but we've gone down. So that's why it's a negative delta H for an exothermic reaction. For an endothermic reaction, overall, energy within the system has gone up. It's absorbed energy from the surroundings. So in terms of enthalpy, you always want to be thinking, how much energy is in the chemical system? If it's gone down, obviously that energy has been released to the surroundings. It's an exothermic reaction, and you've got a negative enthalpy change. In terms of endo, of course, it's the opposite. Couple of questions. Ruhab, is it minus 110? No. Okay. If you did this, if you just put the positive values on both sides, then yes, you would have to remember to make these negative. Okay, so at some point you always do have to remember to make them negative. But for me, I always start with negative numbers in terms of bond forming or bond making. That way, I can just literally line the numbers up in a row and do the sum. Okay, so the biggest mistake students make here is not counting the number of bonds you've got. Okay, correctly. So it's the really simple things. It's not a difficult thing to calculate this, but it's really easy to make small mistakes, because if you miss out one of those OH bonds or something like that, your answer is going to be out, isn't it? Okay. Mimi, if your mean bond enthalpy is given as a positive number, you change it to a negative number for bond making. Absolutely. Yeah, that's what I'm saying there. Okay. So if ever they ask you, what is the mean bond enthalpy for, you always give it as a positive number, because they're always given as the bond breaking. Okay, how much energy does it take to break that bond? So if they ask for the value for a particular bond enthalpy, give the positive number. But when you're working out delta H, all right, you are absolutely 100% safe. Positive values for bond breaking, and literally just put a minus in front of those numbers for bond making, and then it makes your calculation really, really straightforward. Okay, so what I would say is that typically when they do this sort of thing, okay, sometimes they'll ask you to find delta H, just like we've done. But sometimes they may ask you, I'm going to do this in green, to find, ooh, what's the bond enthalpy for a C double bond O? Question mark. Well, I always set it up in exactly the same way. Let's call this X. Okay, it's going to be 2x, isn't it? Because there's two of them. And let's say we have got the delta H for the reaction, which is minus 160. I would still set it up in exactly the same way. All right, I would write out, what was that C double bond O there? Okay, so I write out minus 160 equals 50 plus 150 minus 2x, which is the unknown, minus 250. So what I would do is I'd rearrange it then to make the 2x the subject. I would flip it over the other side to make it positive. So then I'd be going equals plus 160 plus 50 minus 250. Okay, and that would give me my value for 2x. Okay, I think. Oh, a minus 160. Okay, so that'll give me my value for that. Breaking is positive, making is negative. Okay, that's one way of remembering it. I like that. Okay, breaking is positive, making is negative. I like that. I might use that. Thank you very much, Grace. You could say breaking is back. Yeah. Okay, so let's not confuse matters. Okay, so for me, these bond enthalpy questions are pretty. Oh yeah, I did put 160 on the end. Anyway, but that's how you do it anyway. I always like to rearrange things from first principles. I write it out in a way that's familiar to me and then rearrange it. Okay, so that's what I've done there. So, right, next thing. What do we need to do next? Calorimetry. So how are we on MCAT, ladies and gentlemen? How do we feel about this, MCAT? Oh, a little sip while you write it. Yeah. Yeah, so these aren't too bad, are they? Okay. These aren't too bad. Oh, thanks, Miss C. Not too bad. Okay, so we're not worried about this too much. So I will touch on it then. So usually we've got our calorimeter. We've got a known volume of water in there. Now, two things, right? One is to find the delta H combustion of a fuel. Okay, so you've got your fuel underneath with your little spirit burner or whatever it is. And the other one is maybe like I'm going to say delta H reaction. It could be neutralization or something dissolving or whatever. Okay, so this one here would be like a copper calorimeter. This one here would be polystyrene. Okay, so the reaction's going on in here. But for us in this one, okay, so the reaction's going on in here. For that one, you don't want any heat to escape. Whereas this one here, this is where the reaction is, okay, the burning of the fuel. And what we want to do is transfer all of that heat into the water. And that's why this is copper, because we want to conduct that heat into the calorimeter, okay, and into the water. Whereas with the one on the right here, what we want to do is keep the heat inside it, okay? You don't want it to escape. So that's why there's two different things. Yeah, and plus you'd have a lid on there as well. So this calculation here, Q, which is the energy change for the reaction, equals MC delta T, okay? Now the M, one of the biggest mistakes students make is they think it's the mass of fuel or something like that. It is not. It's always the mass of either water or the solution that you have, okay? Now, unless you're told differently, that is 1 gram per centimeter cubed, okay? 1 gram per centimeter cubed. So basically the volume in centimeters cubed is the mass in grams, okay? Is the mass in grams. Mass of solvent also, yeah, either or, okay? So they won't ask you to account for anything else. So that's the mass. So if you've got 50 centimeter cubed of water, it's 50 grams, all right? If you've got 75 centimeter cubed of water, it's 75 grams, okay? If it's aqueous, it's solution. Yeah, absolutely. This would just be water. We always just use water for this delta HC1. This one here would be a solution. Maybe you've got a mixture of HCl and NaOH. Now, when you've got a question like that, be careful, because they say, oh, 25 of HCl was added to 25 of NaOH. Well, the value you use in your MCAT then would be 50, all right, because you've got 50 centimeter cubed of water. Okay, delta HR is delta H reaction. It's like a generic term, delta HR, Benyon. Okay. So C, that'll be your specific heat capacity of water, which is 4.18 joules per gram. Joules per Kelvin per gram. No, joules per gram per Kelvin. Sorry, that way around. Doesn't matter. Now, what does that mean? That means it takes 4.18 joules of energy to heat up 1 gram of water by 1 degree Kelvin. All right. So that's what links. All right. That's what links the mass and why we need the mass and the change in temperature. So this is really a linchpin between those two other things. Okay. Kelvin is the same as degrees in this calculation. Yeah, absolutely. Now, the reason is this, all right? So going on to delta T now, this is your change in temperature, which is usually in degrees Celsius, but you don't have to change the units here for this calculation. The reason being is that the Kelvin scale and the degree Celsius scale are proportional to each other. Okay, so you've got 25 degrees Celsius, that equals 298 Kelvin. Well, 26 degrees Celsius is 299 Kelvin. Okay, 24 degrees Celsius is 297 Kelvin. Now, because we're looking at the delta T, the difference between the starting and the final temperature, it doesn't matter, okay? Because obviously the difference here, the delta is 2. The difference here, the delta is 2. So you do not have to convert, you do not have to convert them. When I say they're proportional, they go up in the same kind of integers, if you like. So just like I've showed you, Raseb. Does that make sense? Maybe I wasn't using the right phrase, but do you understand what I mean? So because we're quoting a delta, okay? Yeah, 273 is 0 Celsius, isn't it? Okay. Same interval increments. Yeah, that's it. All right. So when you're using a temperature, all right, so 25 degrees or 298 Kelvin, it does make a difference because there's a big difference between the numbers 25 and 298. Okay. But because we're looking at the delta, the difference, you don't need to worry about it. Okay. Hopefully that helps. So obviously, once we've found our energy change, all right, then I would automatically, immediately convert it into kilojoules instead of joules, okay? Because your answer is going to be in joules here because of this joules in the specific heat capacity of water, Okay, so turn it into kilojoules. Yep, absolutely, by dividing it by 1,000. And then all we need to do to find our delta H for the reaction is Q divided by number of moles. Now, what is that number of moles? Where do we get that from, ladies and gentlemen? How would you describe where to get that number of moles from? Why is the unit for mass grams per centimeter cubed? No, this is I'm saying that water is 1 gram per centimeter cubed. That's the density. Moles of HCl from the other thing, not water. Mass or MR or copper. Mass or MR of solid. Yeah, I think those are good examples. But generally speaking, where does that number of moles come from? That equals the number of moles of your limiting reagent. Okay, it's the number of moles of your limiting reagent. So here you've got fuel plus oxygen. The oxygen's in excess. So this here is your limiting reagent. So you want the number of moles of fuel that you used. Of course, you probably use the difference in mass there to find the number of moles and so on and so forth. I'll get to that now, Mimi. So here in these reactions, delta HC, number of moles is the number of moles of fuel. When you've got these other types of reactions that are going on in a polystyrene cup, whether it's, if it's dissolving, then it's the mass of solid you're dissolving, or the number of moles of solid you're dissolving. If you've got a reaction like HCl plus NaOH, so HCl plus NaOH gives you NaCl and H2O, of course. What if you've got 1 mole of HCl and 0.5 moles of NaOH? Which one are you going to use in your N to find delta H? 1 or 0.5, or HCl or NaOH? Yeah, good. Absolutely. It's a 0.5 because you have to use that because there's 0.5 of the HCl here that doesn't actually get used. Okay, you can't include it. You can't say those moles, those HCl molecules, contributed to your energy change when they didn't. They didn't get involved in a reaction. They're excess. They're not getting involved in a reaction. So that's why we always say, okay, if you're not told explicitly that one of the reactants is in excess, okay, so if you're told the HCl is in excess, you know to use the NaOH for your calculation. But sometimes they don't tell you, and you have to work out which one is the limiting reagent. Okay, so it's the number of moles of your limiting reagent. Now, why do we do delta Q over N? Well, delta H is always measured in kilojoules per mole. Okay, so how many kilojoules of energy is released in this reaction per mole of reactant? Okay, so Q is in kilojoules. That's it. So you get your answer out of this, and it's joules. What you need to do is divide by 1,000. Okay. That's it. That's it. So your answer is in kilojoules per mole. This is kilojoules. This is obviously number of moles. Kilojoules divided by moles, kilojoules per mole. Okay. So instructions, number 1, Q equals MC delta T. Number 2, divide your answer by 1,000. Number 3, find your limiting reagent, number of moles. And then 4, delta H equals Q over N, and that is in kilojoules per mole. Done. Okay. So we're all on the same page with this. So there are nuances to this. Okay. Energy change is defined per mole, and enthalpy change is per mole. Yeah. Kilojoules per mole, 9 times out of 10 kilojoules per mole. In fact, 99 times out of 100. Okay. Okay. So yes, the negative sign. Okay, the negative sign. Now, what you've got to do once you get your answer is put the correct sign on it. Never, ever, ever write a delta H without a sign on it. So for this reaction, okay, there's 2 ways in which you can do this. Okay, 2 ways in which you can do this. First one, you can look at your delta T. If there's an increase in temperature of the water, then you know it's an exothermic reaction because energy's been released by the chemical system and it's gone to heat the water up. So if you've got a positive delta T, that equals a negative delta H, okay? So in fact, I'll write that in green somewhere. So a positive delta T equals a negative delta H. Of course, a negative delta T, if the temperature's gone down, then that will be a positive delta H. And you just have to remember to put your sign on the end, okay? Yes, you're right there, Ruha. Okay. If we ask for a method for the copper calorimeter, what steps would you use? Yeah, so it's a case of making sure that you're making it a fair test. It's not too difficult. I would basically just say known volume of water, find your mass of your fuel to start with. Okay, so record the mass of that. Then leave the fuel burn, okay, for a set time, so like 30 seconds, recording your starting temperature, then record your final temperature, and then record the final mass of the fuel, okay? So what you've got then is your change in mass of fuel, so in other words, how much fuel you used. You'd also got your delta T, your change in temperature, okay? Yep, that's what I'm going through, Louis. Okay, so that's your method. So that method, you can find that in the content guide under the practical section, methods step by step. There are, of course, a lot of points in here you can drop. So errors that can be included in this as well. We could spend an hour talking about the errors that could be in this one practical. So I don't want to do that now because obviously we've still got a lot to get through. Okay, so onwards and upwards. We have got energy profile diagrams. Yeah, I mean, they kind of, that's what I kind of did at the beginning there, isn't it? Should we get onto Hesss? Anyone fancy a bit of Hesss? Yeah, I thought so. I thought so. Okay. So let's do. What is that? I keep doing deltas. A plus B gives C plus D. Okay, good. It is the indirect route taken. So Hess's law, I won't write it, but my definition, you'll see slightly different ones out there. The enthalpy change for a reaction is the same, or no, the enthalpy change for a reaction is independent of the route taken. Okay, it's independent of the route taken. So just generally speaking, okay, let's say we want to find a delta H for this reaction. There's lots of reasons why we might not be able to measure that delta H for the reaction. All right, it might be that the reaction doesn't actually take place directly. It might be that it's too exothermic. It might be that it's not exothermic enough for us to measure using calorimetry. Okay, so there's lots of different things. Okay. Loch Hess monster. I'm not going to do this with a Scottish accent because I can't do one. But so there's lots of different reasons why we can't measure an enthalpy change directly using calorimetry. Like I said, too exothermic, not exothermic enough. Same for endothermic. It might be that reaction just doesn't happen. So for example, if you took some carbon and some oxygen and put them in a jar together and give them a good shake, you're not going to get carbon dioxide out of it, are you? Okay, it just doesn't happen. It doesn't work like that. So we need to find a delta H for a reaction that we can't measure directly. And this is where Hess's law comes in. Let's say we can measure directly this. So we can turn A and B into X and Y. And we're onto a winner there. We can find that enthalpy change. We can then turn X and Y into C and D. Happy days. We can find the enthalpy change for that reaction. Now, what we're saying here is let's call this 1 and 2 enthalpy changes or reactions. The delta H for the top reaction will equal 1 plus 2. Like literally all we're doing is finding an alternative route around. Okay, it's like when the bus has been cancelled or the train's been cancelled, and you're gonna have to find a different way around. Okay, that's all it is. So Hess's law is just this, but it's just when other things start to creep in that it can get a little bit difficult. Okay, this is not for anything, Raseb. This is just like in general right now. Okay. So there are 3 types of Hess's law questions you are going to come across at AS. Okay, there's using enthalpy of formations, there's using enthalpy of combustions, And then there's really quite difficult ones where they give you a series of reactions, and what you have to do is kind of put them together. And I know that there's some of you guys in the course, you know, whenever I get a Hess's Law question that people take a picture of for me and send it in to me and say, look, I need some help with this. Where do I get started? They are the most difficult ones because you have to look for links between them. We've not got time to go through that today. But what we are going to do is look at the formation ones and the combustion ones, all right, and the ways to remember how to do it. So the first thing I'm going to say here is that, I don't know, let's take a typical reaction. Let's do enthalpy of formation. So let's do CuSO4 plus sodium gives us NaSO4, Na2SO4, and Cu. So that would be that. Okay. Now let's say we can't find a delta H for that reaction. Now, first thing I'm going to say, whether it's formation or combustion, doesn't matter. This equation at the top, ignore what it is. Okay. Ignore what type of equation it is because it can get really confusing. Okay, so if you think, oh, that's the enthalpy change of formation, or that's the enthalpy change of combustion, it really confuses matters. What I would say is just ignore what type of reactions at the top. It's all about the data you've been given. Now, typically you'll get a table. These are a list of some delta H formations. Okay, thank you very much. And then they say, you know, this is find the enthalpy of combustion for a reaction. It's like, whoa, hang on a minute. You have been given formations, but I need to find combustion. The reaction at the top doesn't matter what it is. It could be a neutralization reaction. It could be a combustion reaction. It could be another formation reaction. It doesn't matter. Okay. Just ignore what type of reaction it is at the top there. What you need to do is focus on the information you've been given elsewhere, always in the table. So let's say you've been given delta HFs. Okay. Now, when you've been given delta HFs, so you've been given the delta H formation for CuSO4 and for Na2SO4. Okay. Why would they not give you the enthalpy change of formation data for sodium and for copper? Oh, no worries, Art. You take it easy. Yeah, good. The elements in their standard states. Now, it's really helpful to remember your definition of delta HF and delta HC. Okay, good. Absolutely, you guys are on this. So when you get given delta HF, you need to, okay, intermediates equal your elements in standard states. Okay, so your intermediates go down here. We have got copper, we've got sulfur, we've got oxygen, and we've got sodium. Okay, so S8, I suppose you could call that. You know what? It doesn't matter. Okay, literally, when I do them, when I'm actually answering questions, I literally just write copper, sulfur, oxygen, sodium, yeah, whatever. Okay. Now, next step, arrows up. Okay. What we're doing is we must remember we are forming these compounds. Okay. So arrows will go from our elements in their standard states to those compounds. Okay. To those compounds. So what we need to do, and what we mustn't forget, is find a route around. Okay. So let's say, I don't know, that CuSO4, the formation of that was minus 30, and the formation of this was minus 60. Okay. Now, what we need to do, delta H, okay, does not equal minus 30 plus minus 60. It is. Combustion arrows are down. Yeah, absolutely. So delta H is this. So what we need to do, first and foremost, is make sure that our black arrows are going the correct way. This one here, it's going the wrong way, okay? So this would be minus 30, okay? What we need to do is flip that arrow over to make sure it's going the way we want it to go. So that now becomes plus 30. So plus 30, and then this is minus 60. We don't have to change this one. It is going in the correct direction. Minus 60 equals minus 30 kilojoules per mole. So like I said, I'm just using simple numbers here, okay? So when you've got enthalpy of formation, all right, arrows up, what you need to do then is flip any arrows that are going the wrong way, okay? No worries, Katie, thank you very much. Hopefully see you tomorrow. So that's all we need to do. Okay, so that's the method, if you like, for these Hess's law equations. So using delta HF. Now for delta HCs, okay, what I'm going to do here is if I was, I'll tell you what, I'm going to write, I don't know why I rubbed all that out actually. I'm going to write an equation for carbon plus hydrogen gives CH4. What's that? How would you describe that equation, guys? We're going to have to be quick. We've only got about 4 or 5 minutes. So what is that the equation for? Good. It's for the formation of methane. Okay. So that is actually an equation for the enthalpy of formation of methane. So this is what I was talking about before. Find the delta HF of methane, but then they give you loads of delta HC data. Okay. So for carbon, for hydrogen, and for methane, they give you delta HC data. Okay. What you need to do, okay, your intermediates, the ones at the bottom here, if you're given delta HC data, they equal the products of combustion. So down here, what you'll notice, and this is key, okay, is that these are all the oxides, CO2 and H2O. And what you'll notice is this, that those products there, they are the products from when you actually burn methane. H2O is the product from when you burn hydrogen, and CO2 is the product when you burn carbon. So you get carbon dioxide and water, whichever side you come from. Okay, that makes sense? So again, how do we do this? Well, we need to go this way around. Okay, so which arrow is going the wrong way for us? Which value do we need to flip or invert the sign for? Well, it's this one. This one over here needs to be flipped to go the right way. Okay, that's it. So we're only flipping that one in terms of CH4. Okay, so Hess's law is really useful. I don't think, I mean, they can give you some really tricky questions. Okay, why is it combustion? Because they've given you combustion data. Okay, so let's say they gave you the combustion data of those three, and this is X, Y, and Z, X, Y, and Z. So this would be the delta HF formation of methane. That would equal X plus Y, and you'd invert the Z one because that was going in the wrong direction. Okay. And you do have to balance the products. Okay. You don't have to balance the ones down here, but you do have to account for any balancing up here. So this would be 2 times Y, 2 times Y. Okay. So down here, doesn't matter. You could draw a smiley face in there if you wanted to, so long as you know that they are the products of your combustion of those different things in the main equation. Okay. So we don't ignore hydrogen. We don't ignore hydrogen. Hydrogen burns. Okay. It reacts with oxygen to form water. It's not going to be 0. It is absolutely not 0. Okay. So in combustion, there's only one element that doesn't have a value for delta HC. What's that? What's that one element that doesn't have a value for delta HC, guys? Boom. Thabo, oxygen. Okay, oxygen. So anything else? Now, obviously, that is 49 minutes or just less than that on, well, everything you need to know about enthalpy for AS chemistry, like literally. I mean, obviously things are going to take a little bit more practice than that. But you know, those are the headlines. These are my techniques that I use to teach them. Hopefully they've shed a little bit of light on it and got you to think about it in a different way. So as soon as I finish the lives this afternoon, I'm going to hop onto the content guide. I'm going to unlock, I think, some of the more useful lectures or tutorials within that section. So check that out. I'll unlock the live class as well that I did for Enthalpy. That's great. Thank you very much. What are we doing tomorrow? I genuinely can't remember. I look in the morning. I can't remember what I've planned. Yeah, you guys are just going to have to remind me. Oh, lifesaver. Thank you very much. Rich, how do we know what will be the value at the end? Well, you'll just get your value. You just actually, you know, just do the sum. That's all it is. Literally just do the sum. That's okay. That's all right, Louis. Hopefully that was helpful and you can come back tomorrow for some more. And like I said, if you want to make some notes on this, I'm going to unlock some of the tutorial lessons within the energetic section for AQA and OCR and EdXL. Give me, I don't know, till about 4:15. I'd have done it by then. I should have done it before the class really, but there we go. Hafsa, thank you very much. Okay, the sign at the end will be the sign at the end, Raseb. So it may end up positive, it may end up negative, but you don't have to think about putting the sign at the end. If your calculation is correct, it will be the correct sign. You might end up with a negative number, you might end up with a positive number. Okay. So thank you very much for coming, guys. Make sure you spread the word, okay? We've not got as many people in here as I'd like, I'll be honest, considering there are tens of thousands of AS students around the country not going to school right now. So yeah, make sure you spread the word, please, guys, okay? The more the merrier. It doesn't mean that you're going to get any less attention, just means more students, we get to help more students, okay? So thank you very much, guys. I will see you tomorrow at 2 o'clock for whatever it is we're doing. I can't remember, but I'll see you to do it anyway. So thank you very much, guys. Take it easy.